Hello. We're going to discuss volume of rotation and the cylindrical shells method. This is on chapter 6, section 3. So this idea of finding the volume of a cylindrical shells like this came from geometry. For instance, this is a cylindrical shells. You have an inner cylinder, which is this one, and then you have the outer cylinder, the bigger one. So you have the smaller cylinder that is inside the bigger one, and what we want to do here is find the volume of the space that is between the two cylinders. So we call this cylindrical shells because inside here it's all empty there. So to find the volume of this cylindrical shells, this is what we need. We need the shell height. So how tall is this cylindrical shell? So we call that the height is represented by h. And what is the thickness of the shell? So the space between, the distance between the two cylinders. Okay, so we call that delta R. And we say, so the inner cylinder has a radius that we call R sub I. I stands for inner. And the outer cylinder, the bigger one, its radius is called R sub 0. Now the radius of the cylindrical shells, okay, is the average of the two radii. Okay, so to get, we call that radius of the cylindrical shell as R. So to get it, you have to average the two radius or the two radii. So delta R, the thickness of the cylindrical shell, is basically you get it by taking R sub 0 minus R sub I. So the outer radius minus the inner radius. So to get the volume of the cylindrical shell using geometry, you take 2 pi r. 2 pi r basically is the circumference of the circle with radius r. That's the radius of the cylindrical shells. And then times the h. H is the height of the cylinder. And then times delta r, which is the thickness of the cylindrical shell. So this is how you get the volume of a cylindrical shell. So we can rewrite it here as V equals 2 pi times shell radius, which is R, times the shell's height, and then times the shell thickness. So this is a concept coming from geometry. We're going to use the same concept to understand calculus. Right? So we go to calculus now. We want to discuss case 1. So first we have the data for the region. So they give us the region that's bounded by y equals f of x greater than 0, the x-axis, which has the equation y equals 0, x equals a, x equals b, and a is less than b. And then it said the rotation is about the vertical line x equals h. So, and the question, of course, is to find the volume of rotation by Shell's method. So, let's just sketch the region. Okay, so basically, in two-dimensional, the region is bounded by y equals f of x. That's above. To the left by the line x equals a. To the right by the line x equals b, and below by the x-axis. So it gives us this region R. Now the The line of rotation is about x equals a. This is a vertical line, x equals a. So that's where the rotation is going to happen of this region. Now, when you so now we go back to the definition, the geometry. We want to borrow this idea of geometry in order to find to create the integral for finding the volume of rotation for using the cylindrical shells method, right? So we're going to use this rectangle is what we call the cross-section rectangle. So in terms of cylindrical shells, when we use the cylindrical shell method, the cross-section is not a line as we did with the washer and the desk. The cross-section here is a rectangle. So how do you get that rectangle? You pick an X point between A and B, okay, and then you trace that X point to the curve. That gives you the height, and then from this height of the rectangle, this how tall is the rectangle, and then from that height you draw your rectangle. So this point should be like in the middle of this base here. So X is in the middle, is the midpoint of the base of the rectangle. So you that's how you're going to draw your rectangle. So this is the cross-section rectangle. And another thing that is different from both disk method and washer method is that the cross-section rectangle is parallel to the line of rotation. Recall that for the disk and the washer, the cross-section line is always perpendicular to the line of rotation. But for the cylindrical shell, the cross-section rectangle is parallel to the line of rotation. Okay. So now, we're going to, so what we're going to do, we pick this rectangle. We're going to revolve this rectangle about the vertical line x equals a. So that will sweep a space and create this cylindrical shell. So then we go back to geometry. We know that we need to find the radius of the shell, this cylindrical shell, and the height. We already find the height. The height of the cylindrical shell is the height of the rectangle. So how tall is the rectangle? It starts from the x-axis up to the curve. X-axis basically is y equals 0. That's its equation. And the function is y equals f of x. So the distance between f of x and 0 is f of x. So that gives us the height to be f of x. Now what is the radius? The radius is the distance from x to the line of rotation. So the distance from x to the line of rotation, the line of rotation is x equals h. So this point is h, and this one is x. So the distance between x and h is x minus h. That will give us the radius, because the line of rotation is the sun. It's at the center of this cylindrical shell. Okay, so we get the radius is x minus h. So we write down radius equals x minus h. We know the height is the function f of x. So we have the two data, and then the thickness is how thick is this rectangle. So we call that delta x. Okay. So now we know the thickness is delta x. We know the height is f of x, and we know the radius is x minus h. So we copy those down. Okay, and we call them r of x as the radius of the shell, and then h of x, which is the height of the shell. Now to find the volume of rotation, we're going to use that concept of geometry. We're going to take 2 pi times the shell radius times the shell's height and then times the thickness. Instead of us writing delta x, when you use the integral, you don't write delta x anymore. You change delta x to dx. So this dx kind of represents the thickness. And then to do it for all of those rectangles that rotate in respect to the line of rotation x equals h, we're going to use the integration. So we're going to integrate from a to b. Integrating from a to b is because the region is bounded by a and b in terms of the x, in terms of the x limits. We call those limit of integration. So again, when we get this more general formula of the volume of rotation using the cylindrical shells method, so then we can just replace shell radius, we got it to be quantity x minus h times shell height is f of x and then a dx, and then we take the integral from a to b of everything. Okay, so that's basically the concept here, and I will stop and do the example next. Thank you.